So this is who I am, Charles Radley. About half my career has been in aerospace and about half my career is in information technology. I've worked NASA contracts. I've done a lot of failure analysis and QA, and I think of myself as a professional pessimist. I try to brainstorm what can go wrong with complicated systems. And as a result, it's been a fun career because I've learned a lot about all kinds of different parts of spacecraft and space technology. You know, I've worked with companies like Hughes and Lockheed and British Aerospace, and for a lot of projects I had the title of safety engineer. And as a safety engineer, I've had the right to, I can poke my nose into anything, and I can go into anybody's office and I can say, hey, what are you doing? Because I can say that might be a safety problem, so tell them what you're doing. And I've had engineers explain to me all kinds of cool stuff about spacecraft. And sometimes there's a safety problem and sometimes there's not. And so you'll find me on Facebook. We have a page, a Lunar Elevator page on Facebook. I'm on LinkedIn. I'm Vice President of Leeward Space Foundation, so we have a group on LinkedIn, and I'm on ResearchGate, and I'm on academia.edu, and I welcome email. So how does this work? Like that? That was obviously not what I intended. Do I do left, right? Right click, okay. Okay, so Lunar Space Elevator, sometimes we call Lunar Space Elevator infrastructure. Okay, so there's a lot of talk about, or there has been a lot of talk about, building a space elevator, a beanstalk from Earth to geosynchronous orbit. The current state of the art is basically that's impossible. Theoretically, it could be done with carbon nanotubes. I'm not holding my breath, frankly. I think it falls in the same category as nuclear fusion. I'm not holding my breath for it. I mean, for nuclear fusion, we've been 10 years away from break-even for the last 50 years. And I think we're in a similar situation with carbon nanotubes. So I'm going to be blunt on that. But the concept of a lunar elevator is more recent. And the exciting thing is that we can actually build one today. There are now materials on the market which are perfectly strong enough for building a lunar elevator. Essentially, a lunar elevator is a tether reaching upwards from the surface of the moon to a Lagrange point, typically to, well, it has to be either EML1 or EML2. The EML1 is between the Earth and the moon, and EML2 is 180 degrees opposite behind the moon. And the tether is kept taut by a counterweight, quite a small counterweight. Actually, you don't need a counterweight, but we'll probably have one anyway. And there's so you've got the Earth space elevator relies on centrifugal force, but the lunar elevator not so much. The lunar elevator gravity field is much less, so the centrifugal force is fairly small. So what we find is that I'll show you with some diagrams. Although the EML point is about 55,000 kilometers from the surface of the moon, we have to extend the tether way beyond that to get enough centrifugal force to balance it. So the numbers are pretty mind-boggling, but the numbers pencil out, and believe it or not, it is possible to build one. Okay, so a quick visualization. The moon, the counterweight, the Earth, the tether, which ends, the counterweight is probably, this is not exactly to scale, but the counterweight ends up being about halfway between the Earth and the moon. And I've collaborated a lot with Liftport Group on this. Okay, here's some numbers. The delta V budget, getting from A to B in the Earth-Moon system. But getting to the EML point is easier than getting to geosynchronous orbit, and it's easier than landing on the surface of the moon. And it's a good base of operations. It's also less than what you need to get to an Earth-crossing asteroid in most cases. So here are some of the numbers. Again, this is not exactly to scale, but this was a design that Marshall Eubanks came up with for Liftport Group. and it's you see the distance from the Lagrange point to the moon is 55,000 kilometers, and the distance from the Lagrange point to the counterweight is 195,000 kilometers. Pretty big numbers, but the numbers say that it'll work, and we can do it with existing materials because the forces are so low. And in this case, the counterweight is actually closer to the Earth than to the moon. Okay, material selection. There are 4 or 5 materials which we can use to build a lunar elevator. I've got a sample of one right here. So you're welcome to pass this around and play with it. That material is called Dyneema, which is made in the Netherlands. And that material is so valuable, so rare, and so expensive that a company in Spain sent me that sample for free. This stuff is cheap. Other materials, there's Xylon, Kevlar, Spectre 2000, and I neglected to put on that list carbon fiber T1000G would also work. Kevlar is kind of marginal. You don't get much payload with it, but other materials are better. Xylon comes from Japan, from the Toyobo company. Dyneema comes from the Netherlands, from the DSM company. So most of the calcs that we did at Litport were based on Xylon material. Oh, there's another material. Oh yeah, at the top right, M5, Magellan M5. That is actually the world's best material in terms of strength to weight ratio. It's fairly new. It came on the market about the year 2000. But they're having difficulty mass producing it. It's so strong that the tooling they use tends to degrade very rapidly. And it's currently made in the US by the DuPont company. DuPont bought out Magellan, and most of the production is currently bought by the US military for making bulletproof vests and helmets. So there's very little available for commercial use. But Xylon and Dyneema are widely available for commercial use. And yeah, and Eagle was telling me at lunch that Toyo company could produce another version of carbon fiber better than T1000G fairly easily, but currently there's no demand for it. Again, theoretically, carbon nanotubes would work, but they're not available. Not as commercial products, not in pure form. There are a lot of materials that have carbon nanotubes mixed in, but you don't really get the benefit of the pure single-wall nanotube in those configurations. So, we've run the numbers. Now, there have been some studies. The concept was the first document where we know somebody wrote it up was in 1910 by Friedrich Zander in Latvia. He never published his notes, and he died in his 40s. But his notes were discovered and published in 1977. And one of the people that saw those notes was Dr. Eugene Levin in Russia. He moved to the US and joined Star Technologies, Jerome Pearson. And they did a NASA-funded study in 2005, funded by NASA Institute of Advanced Concepts. That was the first study, but the design they came up with, although feasible on paper, it was way too big. Their design was weighed 7,000 tons, which is bigger than we would need in the near term, and also bigger than we could possibly deploy. So a Litport group has come up with a design that's a lot smaller, and that could be buildable in the near term. But yeah, it needs to be tapered. The tether has to sort of start out thin, get broad at the L point, and then taper to be thin again. Okay, so some of the key figures of merit. This is interesting because it reduces the cost of access between the L1 point and the lunar surface, which currently is very expensive. It's very expensive to soft land on the moon, and it's even more expensive to lift material from the moon using chemical rockets. Some interesting points of note. There's a region, the first 5,000 kilometers from the surface of the moon is where the gravity is the highest, and that's where the climber has to work the hardest. The climbers are solar powered, and they'll climb up. And what Eubanks figured out in his numbers is that once you're above 5,000 kilometers, the stress, the tension that you're loading the tether with drops off dramatically, and you could actually send up a second climber with a 7% payload reduction. And you can keep doing that. And so you can have up to 6 climbers simultaneously going up the tether, separated by 10,000 kilometers. Now, there's a big debate is how fast can you go up and down the tether? Opinions vary quite widely. Jerome Pearson and the NIAC team, they were saying, well, we better stick around 15 meters per second, which is very conservative. But it's also so slow that it takes forever to get a reasonable amount of payload delivered. There's another group in Israel, a student group which has disbanded, but I'm still in touch with them. They were out of Technion University in Haifa at the Asher Space Institute. Led by Dr. Alexander Kogan, who is a former Soviet scientist who worked on the Soviet planetary missions. And they figured you could get up to 700 meters per second. And the limitation is really the speed found in the tether material. If you start to go much faster than 700 meters per second, then you get close to the speed of sound, and then you can get shock waves which will tear the tether apart. The speed of sound varies. They were assuming the material Magellan M5. But at 700 meters per second, it only takes you a few days to get from the surface of the moon to the L1 point. And I was playing around with it on a spreadsheet, and I figured that you could do 80 climber trips per month at that speed. Each climber, so in this configuration, our 48-ton minimal lunar elevator, the climbers each have a payload of 100 kilograms, so we can deliver about 8 tons per month soft landing onto the lunar surface, and we can lift another 8 tons per month coming off the lunar surface. So the system, in terms of launch costs, the system pays for itself in about 1 month. There are two, we could have a single elevator, but that problem is you can only have stuff going in one direction at a time. You could actually have two elevators side by side, and take advantage of Coriolis force, because Coriolis force means as you go up the tether, you tend to get pulled to the west, okay? And as you go down the tether, you tend to get pulled to the east. And so if you have the downwards tether to the east and the upwards tether to the west, then the Coriolis force will keep them apart and they will not interfere with each other. Oh, this is my spreadsheet on the number of climbers. I played around with different velocities, and I figured how many trips. This is not actually the number of climbers. This is the number of climber trips you could get in a 2-week period. I was thinking of a single elevator, so I wanted to get everything up in 2 weeks, reverse the flow, send everything back down, and keep going on. So game-changing cost reduction. I don't really have good numbers on the cost reduction. So these are conservative numbers, and nobody's really analyzed the cost in sufficient detail, and I really wish somebody would release a few tens of K that some people could study this, but so far it hasn't happened. Taking it in terms of simple launch cost, a rocket can deliver, any rocket, doesn't matter, Falcon, Titan, Delta, whatever, can deliver 3 times as much payload to the EML-1 than it can soft land onto the surface of the moon, okay? So that means, as a minimum, we get a 3 times reduction in soft landing cost, because all you have to do is get your payload from Earth to the EML point, and then you can land on the moon for free, essentially. And similarly, to recover material from the surface of the moon is 3 squared, which is 9. The lunar elevator gives us a 9-fold reduction in the cost of retrieving material from the surface of the moon and taking it out to the EML point. You can also take material from the moon to Earth or to low Earth orbit. You can deliver it anywhere in the Earth-Moon environment. My intuition tells me that we can do a lot better than that, but I can't prove it. Not right now, not until somebody does some more detailed cost analysis. I mean, you have to look at things like the capital cost of designing, because it's not that simple. I mean, a rocket that launches stuff to EML, it can't soft land anything up to the moon anyway, because it needs to have a soft lander stage with a throttleable engine and all that stuff. So there's a cost to develop all that hardware. All that cost goes away when you've got a lunar elevator. So throughput, I've already mentioned. Okay, well this is for up trips and down trips. So you can have 80 trips of 100 kilograms up and another 80 trips down, giving you 60 tons total, 16. Investment and payback time. So with a 3 times ratio, a 48 ton LSC is equivalent to 16 tons on the lunar surface. And a 9 times ratio is equivalent to 5.3 tons of sample return. So if you've got 48 tons with 100 kilogram capability, that's 5.3 tons divided by 100 kilograms. That gives you 53 payload cycles, and that's how many payload cycles you need to pay for itself. So I can get 80 cycles in a month, so it can pay for itself in a month. This is just in terms of launch cost. I don't have any other way of evaluating it at this time. This was the NASA NIAC. Okay, so this is the cover sheet of the NASA NIAC report done by Jerome Pearson and his team at Star Technologies in 2005. This is so far the only time that NASA studied it. They did get this phase 1 NIAC award. We have tried at least twice, I think 3 times, but I know we've tried twice for a phase 2 NIAC, and we've been turned down each time. Well, we were turned down the first time. Jerome invited me to be a co-investigator with him, so my name's on the most recent phase 2 request, and we're waiting to hear back. I haven't heard whether we've been approved or not, but I'm not holding my breath, but maybe. So after the Pearson team published their report in 2005, I ran across this group at Technion University in Israel. They had a project, they called it Jacob's Ladder. And they came up with a design that was much smaller than the Pearson design. Their design weighed 250 tons and had a payload capability of 500 kilograms, which is getting to be more realistic in terms of something we could build today. I've had a lot of discussions with these guys. Alex Tchaikovsky and we chat fairly frequently. Alexander Kogan, he's retired, he now lives in Canada. I've chatted with him a little bit, a very interesting gentleman. They published some stuff on the internet, which I ran across, but they did not publish, at first they did not publish their full report. I asked for a copy of it, they sent it to me, it was written in Hebrew, and I don't speak Hebrew, so I asked, Alex, any chance you could translate this into English? He said, sure. So 2 weeks later, he sent me an English version, and then but he's not a native speaker, so I kind of proofread it for him and massaged the English, and now we're sort of freely available. I've got it on my little personal website. And it's interesting. It's got all the math, all the equations. Okay, at this point, Andreas, could we maybe play the video? Is that accessible? Yeah. Hello. Oh, that's good. So I collaborated with Liftport Group, and they produce a nice video, so I thought I'd share it with you. It lasts a few minutes. This is up on YouTube. But the idea is our lunar elevator package can be launched on a single launch, at least a single SLS launch, or it could be put onto a Falcon Heavy using electric propulsion. In this baseline, we assume electric propulsion, which takes it out to the EML location. And this package weighs 48 tons. So the rocket upper stage, that becomes our counterweight. So that's the EML station there. We drop a surface attached fixture down to the moon. The rocket backs away, so there's a tether that attached to the rocket. So the rocket goes back towards the Earth. The attached fixture on the right goes down towards the surface of the moon. We might have some Bigelow-type inflatable modules. There's the climber sitting in the middle. That's solar-powered. So the first thing we have to do, we have to deploy that attached fixture down to the surface of the moon. The EML station, deploy some solar panels and gets ready for operation. And there's the attached fixture. And it comes down and it touches the lunar surface, and then it drives little screw penetrators into the regolith. It goes down maybe a couple of meters. It does not have to react very much force. The tether is loaded slightly in tension, and there will be some lateral forces due to oscillations. Hopefully, there will not be too much oscillation. That's, again, something that needs to be analyzed. There are a number of technical challenges. Nobody said this was going to be easy. It's not child's play, but it's doable. And at this point, I am not aware of any obvious showstoppers. There's a fairly long list of technical challenges and technical problems that need to be solved. So once the surface attached fixture is properly embedded, then the climber kicks into action and starts going down the tether, and you see the red wheels going round and round. Now, on the way down, we do not need any electric power. On the way down, we're losing energy, so we need to apply brakes. So we actually don't even need to bother to deploy actually, we will need to deploy the solar panels to drive electric propulsion to counteract the Coriolis forces. But other than that, we can use regenerative braking on the way down. One interesting little thing is, so what it means is we could come down during the lunar night. During the lunar day, we can only go up during the lunar day because we need the solar power to get up. But on the way down, we can come down during the lunar night, and we can actually deliver energy to a moon base because we can use the regenerative braking to charge batteries, or we can even use it to melt blocks of molten salt, like what they do in solar power stations, and deliver blocks of hot molten salt to a moon base to power it during the lunar night. So in this configuration, the lift port guys are of the opinion that one of the first things you have to do is collect a whole bunch of lunar regolith and dump it onto the surface attached fixture to provide additional kind of ballast weight to hold it down. I'm not entirely sure that's necessary, but it couldn't hurt. So this is the little robot design they came up with. Now I'm going to talk some more about some of the resources we can get for the moon. Why would we want to go back to the moon? I've been trying to think of this as a business. The lunar elevator, how can it pay for itself? What kind of revenues can we generate? And we can do lunar mining. I'm going to talk about Helium-3. As Al mentioned, there is a commercial market for Helium-3 today. Because Helium-3 sells for about $1 million per ounce currently, and I estimate the market size is about 100 million a year currently. It's very difficult to get good data, but that's the order. So here you see hoppers on the surface attached fixture, which are getting filled with lunar regolith. And then in a little bit you see it start an upward trip. So there's basically 2 or 3 kinds of destinations where once you leave the lunar surface, there's 3 places you can go really. You can either go to the EML point and stop there, and then you can do transfers to the other Lagrange points or other lunar orbits. Or you can keep going. In this scenario, we go beyond the EML one, and it releases little, the payload is released with little rocket pods, little rocket modules, and they head to Earth. And the rocket modules are just needed to trim the orbit just a little bit to make sure that the perigee is in the right place. The lunar elevator will get you into an elliptical orbit towards Earth. You can either enter the Earth's atmosphere and get recovered on Earth, or you can go into low Earth orbit and rendezvous with a space station. So that's 2 of the 3. The other third destination you can have is for a far side lunar elevator, which I'll talk a little bit about. The counterweight extends away from the Earth, and you can actually get an injection onto an interplanetary trajectory. So you can get a 700 meter per second kick to go to Mars or asteroids or somewhere like that. Not sure how much longer this video is going to run. I think the key points have been made. I think it's coming to a close. All right. Yep. Well, I guess this is partly to show that we've put a fair amount of thought into how this would work. So it's not just a totally off the wall idea. Okay. Can we go back to the PowerPoint? Okay. Major components of the lunar elevator. The counterweight helps keep the string taut and shortens the length. There's the attached fixture, there's the EML station, and the tether itself. So we've done a little bit of design work on the landing platform. Just done some little sketches of what it might look like. Would probably need retro reflectors to get it aligned properly. And we need to figure to get to 1 meter depth. We need an impact velocity of 10 meters per second. So we're going to have to, if we could drop penetrators down from 30 meters height above the moon, that's probably sufficient. One of the various technical challenges. One of the technical challenges is micrometeorites. Up in the lunar vicinity, there's really no man-made debris to speak of, and there probably will not be for a good many decades, probably centuries. But there is definitely a flux of natural micrometeorites, and we estimate that the elevator will get hit and severed about twice per year. So we need to figure out a way of dealing with that. There are some designs for damage-tolerant tethers, like this one from the Hoyt tether from Dr. Bob Hoyt at Tethers Unlimited. So it could tolerate, it has sort of a multi-stranded tether, and it can tolerate individual impacts. And then from time to time, we're going to have to repair these damaged segments. And from time to time, we could probably just restring the entire tether. It would not be that expensive to do that, because believe it or not, the tether material itself is possibly the cheapest part of the system. The raw tether material itself would probably only cost about $20 million, which is about 5% of the entire system cost, according to our back of the envelope calculations. Oh, okay. Have I been, okay, I thought I had like 45, how long have I been going? Okay, all right, well, I'm probably only about halfway through what I wanted to say, but we could put an elevator on the far side, as Chaim said this morning, we'd use it for radio astronomy. Could comparison of different string materials. I guess you can look at the charts on the website. The far side, this is the picture of where the far side attach point might be from Apollo 11. I wanted to talk a little bit about Helium-3 because people don't know the deal there. I recommend this book, the Lunar Source book, gives you a pretty good idea of what the moon's made of. We can get from the moon, on lunar meteorites currently sell on eBay for a few $100s a gram. We can make money by just selling raw moon rocks. Okay, Helium-3 is selling on Earth for $1 million per ounce. People are buying this stuff. It has it has one very interesting property is absolutely the best material known for neutron detection. So there is a booming business in neutron detectors, and they use Helium-3 now. Helium-3 does not exist in nature on Earth. It was the byproduct of thermonuclear weapon production. And after the end of the Cold War, the quantities of Helium-3 that were available have rapidly diminished, and demand has increased, and is currently rationed. In 2010. The Department of Energy and the White House and the Congress decided to stop selling it in an unlimited way. They were selling 100,000 liters per year, and they're now rationing it down to 14,000 liters a year. The stockpile, we probably may only have 20 or some years left in the stockpile. And so it's big business. A lot of people want this stuff. So irregardless of nuclear fusion, there is definitely demand for it. It's available on the moon. This is the map from China. The Chang'e 1 spacecraft made a map of the distribution of Helium-3 on the moon. There are other things we can get from the moon, but I'll skip that. I did want to finish with one little story, though. You see, this is the Sea of Tranquility, one of the richest deposits of Helium-3 that we know of. And the richest sample that we currently have was from Apollo 11. The very first moon landing remarkably landed in one of the richest parts of Helium-3 on the moon. And we were completely unaware of it at the time. And at the end of the first EVA on the moon, Neil Armstrong had one sample box left. He had like 5 minutes to get back into the lunar module. He didn't have time to go hunting for any rocks to put in it. So he just grabbed his shovel and started shoveling regolith into it, just as much regolith. He filled it up with regolith, slapped it shut, went back into the lunar module, and that sample is the richest sample of Helium-3 ever discovered to date. But we can make money doing that, and there's a lot of other ways that we can make money on the moon, but I guess I'll wrap up at this point.
Well, I just want to have some time for questions.
Yeah, sure.
So, are there some questions for Charles?
Yeah.
Great. I mean, this is definitely interesting.
Yeah, I can ramble on all day. So.
For sample return missions, 100 kilograms is obviously very useful, but for getting a person to and from the moon, 100 kilograms seems a little bit light for a person and a life support system. Yeah. Does the methodology scale linearly or usefully so that you could move a crew capsule up and down?
Yes, absolutely. It pretty well scales. I'm not sure if it's really linear, but it scales. We'll say we've got three data points. We've got a 7,000-ton lunar elevator that Pearson designed that has a payload of about 20 tons. And then there's the 250-ton elevator, which Technion designed, which has a payload of half a ton. As for manned missions, one of the interesting things to think about, and I'm currently in the final stages of writing a paper for the ARAA Orlando conference next month. And I did some failure analysis because, my professional background includes a lot of failure analysis, and I thought, let's do an FMEA on this thing. And I've been trying to think, what are the abort modes? Because one of the scary things is if you're an astronaut and you're halfway between the moon and the L1 point and the tether breaks, that's not good. What kind of abort scenarios do we have? And we're probably not going to have much in the way of rocket propellant on board because that would defeat the object of the whole thing. The rocket propellant, that starts making it expensive. So, and I've thought of things. There'll be 6 climbers on the moon, so you can actually tether them together six climbers on the tether, and you can have a secondary cable, which is sort of a backup cable, and you could probably catch it. The first 3, maybe 4 on the tether, you could save. The other 2 would probably fall back to the moon, and they would either be lost, or if there's human cargo, we would need to put some kind of a little rocket in there where they could survive a fall from that height. But so I don't think we want to put astronauts on this from day one. We want to get some experience and confidence and learn. But I think the bulk of the business is going to be in non-human cargo. I think that's where the bulk of the money is going to be anyway. So, go ahead.
Do you know how much regolith you have to process to get an ounce of H3?
Excellent question. There's a group at University of Wisconsin that are really the experts in that. I don't have the numbers off the top of my head, but they've published a lot of data on that. But it's a lot. It is quite a lot. It's something like you have to excavate a square kilometer down to about 10 feet to get a kilogram of helium-3, something like that, if my memory serves me correctly.
Charles, regarding the mass of the cable, the tether, I seem to recall reading that for an Earth-based space elevator, suggestions were that the mass was so great that there were proposals of nudging an asteroid into geostationary Earth orbit and fabricating the cable, the tether material, in situ. Is the situation different for a lunar-based tether, or are suggestions that you essentially transport the Xylon from Earth to the Lagrange point?
Yeah, the whole point is for the first prototype and probably the first couple of generations, it would be entirely fabricated on Earth and shipped from Earth up to the moon, because we currently don't. It's a chicken and egg thing. There's no infrastructure on the moon, so we don't have any way of building anything on the moon right now. And I want to get this going today, and this is the quickest way I can get it done today is to buy a bunch of Dyneema from a catalog and get all the mechanical stuff, put it all together, put it on a rocket and get it up there, and I don't need anybody else's help. It's completely self-contained. But the Earth space elevator, I'm not a big fan of that because you need the carbon nanotubes, and I've heard this idea of using an asteroid, but I don't know how you can get carbon nanotubes out of an asteroid. It's hard enough to make them on Earth, let alone out on an asteroid. So I don't think that proposal has been thought through. So. Hello.
Bill.
Thank you. All I remember from college chemistry is that helium is an inert gas. Now, this is a certain isotope of helium?
Yeah.
Free atoms?
Exactly, yeah. So there's in nature
Mixed in
there's
with the regolith or what?
Let's talk a little bit about that. There are in nature 2 stable isotopes of helium, helium-3 and helium-4. All the helium you find on Earth is helium-4, and that's in party balloons and all that stuff. And that's also pretty rare, but helium-3 is much rarer. Helium-3 was discovered in the sun through spectral lines. It was discovered remotely, and there's this really weird stuff called helium-3, and they found spectral lines, and they figured out what it was, even though nobody's ever had any of it, because it didn't exist in nature. On the moon has no magnetosphere and no atmosphere, so it's completely exposed to the solar wind, and the solar wind is very dense in helium-3 nuclei. The helium-3 nucleus is 2 protons and 1 neutron. Okay, so these ions are being expelled by the sun, and they're collected on the moon. And you see that map of the different areas on the moon, which the Chinese. By the way, the Chinese have published a lot of data from their spacecraft. It doesn't seem to be widely appreciated, but there are many countries that have published data. The Chinese have published their data and they use a microwave instrument to map the distribution of these deposits on the moon. There's a mineral on the moon called ilmenite, which only exists on the Maria. And it's something to do with the molecular size of the separation between the molecules of the ilmenite mineral are exactly the right size and shape that a helium-3 nucleus will fit in there exactly and will stick and bond to it. And so this ilmenite mineral just soaks up helium-3.
Again, I'm not a chemist, but this kind of sounds like when Oak Ridge was trying to separate U-235 from 238.
Yes, so
Similar to
yes.
that?
So there is definitely an isotope separation process required. That's a little tricky. Probably the process basically works. There's a lot of volatiles locked up in lunar regolith, not only helium-3. And one of my slides talks about that. There's hydrogen, there's even water, there's carbon monoxide, carbon dioxide, methane, even a little bit of nitrogen. And then there's a fair amount of helium-3. So it's all mixed up in this cocktail of stuff. So you have to use something like fractional distillation to separate out all the different components. And then you end up with the helium, which probably has the lowest boiling point. So it's probably the last thing you're left with is the helium after you've frozen out everything else. And then the lunar helium is not pure helium-3. It's a mixture of helium-3 and helium-4, and it's actually a ratio of 3,100 parts to 1. So you have to use isotope separation. Harrison Schmitt, the Apollo 17 astronaut, has written a book about it, and he talks about that. Apparently you could use centrifuges, but there's an easier process called the superleak process. I don't know much about it. There's not been much published about it. I believe it's somewhat sensitive because it's used in nuclear weapon production, so the US government doesn't publish. They don't want it widely known how to do it because it could be used for other nasty things. But there's technology out there to do it.
Once the landing platform hits the lunar surface, what forces act on it to move it around, and why do you really need to fasten it down?
Okay, so we will intentionally put a small amount of tension on the string just to keep it stable. We don't want it flopping around too much, so a little bit of tension, not very much, maybe a few kilograms, something like that. And then, well, any string tends to act like a guitar string. There will always be oscillations. There's no way of damping them out completely. So as the tether goes up and down, there'll be longitudinal oscillations, transverse oscillations. A big source of horizontal oscillations is going to be the residual Coriolis force. Experience what?
Is there any experience that shows that? Is that just an estimate from a model?
Oh, well, we can calculate it pretty well. The laws of physics are pretty well known. It's the Coriolis. I have a... Oh, let me talk about this little chart. Well, I can come back to Coriolis force. Another thing we can get from the moon is rare earth elements, creep. There are 4 places. This is a map of the moon made by the Lunar Reconnaissance Orbiter. There are 4 spots on the moon which are very rich in a material called creep, which does not exist on Earth. But it's probably a pretty good ore of rare earth elements. And this one is the crater Lalande, which is pretty close to where we would anchor a lunar elevator. So that's when I get the lunar elevator hooked up, I'm going to make a beeline for the crater Lalande. We can probably get rare earth elements from there.
Question?
This is a lunar meteorite which fell down probably 30,000 years ago. I don't know how they did it, but these guys from the University of Bern in Switzerland, people find lunar meteorites in Antarctica and in the desert, all right? And this is one they found in Oman. This is the richest sample of creep that we've discovered, and they know that this came from the crater Lalande. I don't know how they know that, but they're pretty insistent that that's where it came from. Yeah, but Coriolis forces, the equations are quite well known, and the problem, what we don't know is how well the climber will perform, because what the climber has to do, the climber has to damp out the Coriolis forces as it goes up, and if it perfectly damps out the Coriolis forces, we shouldn't get any vibrations at all. But we know it's not going to perfectly damp them out. So there will be some residual Coriolis forces, which means that the tether's going to get kind of pulled from side to side a little bit as the climber goes up. That's going to induce oscillations and waves up and down, and that's going to pull on the surface attached fixture. I don't have numbers for that, though, not yet.
probably the biggest competition you'll have in the future, if it's a possibility. There's a lot of different technologies that they're being tested now with beam technology, like tractor beam technology, pressures. Have you researched any type of beam technology to utilize the same kind of effect that you're trying to do with a tether?
Power beaming. Well, I don't know what kind of design. I mean, I'm quite interested in power beaming, and I've studied it quite a bit. But it's quite expensive, I mean, do you have a specific? There are several designs out there. You mean like a thermal rocket where you shine a laser at this and a bunch of hydrogen comes out? That one? Yeah. No. Some of them may end up being somewhat cheaper than chemical rockets, but they're not there yet. Right now, my competition is chemical rockets and also electric propulsion. There's a whole other discussion about using oxygen for the moon as a propellant. That's a great market, but electric propulsion would be competition to that. Power beaming might become competition one day, but I'm looking at today, and my competition today is chemical rockets.
Any other questions? Yeah. Okay. How about a hand for Charles Radley?
Yeah. Okay, thank you.